Welcome to the Digital Enterprise Society podcast, addressing all aspects of the digital enterprise, inspiring connection without boundaries and creation without limits. Thank you for tuning in. Here are your hosts, Thom Singer and Craig Brown.
Hello, and welcome to, or if you're a return visitor, welcome back to the Digital Enterprise Society podcast. Thank you so much for coming along on the journey of this show that is designed to be a resource for those who work in and around PLM. The Digital Enterprise Society is a forum for the exchange of ideas surrounding the tools, processes, and practices used across the product lifecycle. To learn more, visit us at digitalenterprisesociety.org. My name is Thom Singer, and I have the honor to co-host this show with Craig Brown, an industry veteran and former PLM leader at General Motors. Hey, Craig, how are you doing today?
I'm doing great, Tom. Good to hear your voice. Looking forward to our next guest. A little bit different today in the area of simulation and prediction. So we'll get to it here in a second.
Well, that's what we try to do every week. Our goal is to bring everyone who listens interesting interviews and other ideas that is going to help everybody enhance and grow their careers. And today is going to be one of those shows. We have Greg Thorwald. And Greg is a principal consulting engineer with Quest Integrity out of Boulder, Colorado, which is one of my favorite cities in the whole country. So Greg, welcome to the Digital Enterprise Society podcast.
Hi, Tom. Hi, Craig. Good to be talking with you this morning.
Good to be talking with you. So can you give everybody a little bit of a background of sort of your career, where you started and how you got to Quest Integrity and what you do in your role?
Sure. Since I really enjoyed math and science in school, especially physics, in undergrad, I pursued learning about physics and then got into engineering, discovered I really liked engineering, and as you go through college, you discover there's a lot more to learn. So that led me on to grad school and at CU Boulder, so that goes back to coming to Boulder. And they had a scholarship, and that was in aerospace engineering, so I pursued that. And there was a lot of computational work, the finite element analysis of structures, and I really liked that. So the computational part has been there for a while. And during that time, toward the end of grad school, I met Ted Anderson. He's well-known in fracture mechanics. He has a well-known, widely used textbook. And so I've been working with him for many years. And through acquisitions and mergers, I'm now part of Quest Integrity. And that company does a number of things. They do pipeline inspections, on-site inspections. We have metallurgists. But I'm in the engineering group in Boulder, Colorado. And that's really where we're doing the computational analysis for fracture mechanics, the topic of fitness for service. There's an ASME standard that covers all these different kinds of damages, how to assess those in structures. And so that really connects the digital world of analysis to physical machinery at plants.
So, Greg, this is interesting. And a lot of folks we have on this show are product development people. It sounds like what you're talking about with fracture mechanics, it's more of an operational thing to be able to predict when to service something. Is that right? Or is it also product engineering?
Well, I think it can be two things, and maybe it helps to distinguish between the crack initiation prediction in analysis and what I would call crack propagation or large size crack analysis. So
Okay.
I think for the product development designers, I think they would tend to use more of a crack initiation type analysis. So think of the automotive industry as an example, where if a crack shows up in your vehicle, that's disastrous. And maybe the wheel doesn't fall off, but you don't want to see a crack. So I think the automotive would be very interested in crack initiation. If students or new engineers, if they've seen the SN data, stress versus cycle type data, that's where that is coming from.
Right.
But then as a product is in use, maybe for a few years or many years, since all these metal structures have initial defects in them, those tiny microscopic defects can get bigger and bigger. Eventually you'll have a crack that's 1 or 2 millimeters in size. And that's a different kind of analysis. So if anybody's looked at fracture mechanics textbooks, you'll see this stress intensity factor. you want to compare that to the material toughness, and that will allow you to predict the failure of the structure. So there's a few different methods that we use, but that does tie into the finite element analysis and using metallurgy data to bring all that prediction together.
And then as you predict a failure is imminent or likely within the next few years, does that lead to upgrades, maintenance upgrades, or disposal? I mean, what do people do with that insight?
Right. So I would say that the two common questions that we get if somebody needs help with fracture mechanics analysis, that they found a crack in their weld in their structure and they get upset about that, the first question is that crack going to cause an imminent failure? And if it's not going to break today, the second question is, how soon is that going to break? Is there some kind of cyclic loading? The pressure is going up and down in their vessel. How fast is that crack growing? Do they need to shut it down immediately for a repair? Is it not that bad? Could they maybe wait until the next maintenance cycle a year from now and just keep an eye on the crack? So it really, I think to answer your question, it really depends on the severity of the crack, what the structure is, and will they need to do a repair? Will they need to do some kind of in-service reinforcement? You could imagine putting a patch or a reinforcement on a structure. Or is it so bad that the cost and time to repair it is so high, maybe you just replace it?
So
yeah.
So how do you find these cracks? There must be instrumentation of some sort that helps isolate where the molecules are starting to come apart, assuming it's at that level.
Right. Right. There's a number of different techniques that our inspectors use. Ultrasonic testing works really well. Okay. That can help. Even visual testing. There's what you would call magnetic particle or dye penetrant methods, where if you clean the surface and you smear this dye penetrant over it and wipe it off, and then you use an ultraviolet light, the crack will show up as a bright little purple line on the structure. Sometimes X-ray is used. That'll get you a more detailed view. That's more costly to do that, but sometimes that's needed. So yeah, there's a wide range of techniques to identify and locate those cracks.
Well, and I'm thinking of a pipeline underground, but there must be a way to do that as well. You must send a sensor out in a robot of some sort.
Right. Yeah. In the pipeline world, they use what's called a smart pig.
Yeah, pig. You'll have to describe that.
Yeah, if people aren't familiar with pipelines, a pig is a device that you would send down a pipeline. Often it's within the flow. They don't all have to be smart. You can have less smart or dumb pigs, maybe just to do cleaning, that are maybe scrubbing and removing buildup on the inside of the pipe. But the smart pigs will be equipped with sensors. Again, it might be a magnetic type sensor or an ultrasonic sensor. A lot of our smart pigs use ultrasonics in the flow. So if it's in a liquid, a fuel, an oil, something like that, that'll transmit the UT signal from the device to the pipe wall, through the pipe wall, and give you a return. So you can see bulges and dents in the wall thickness and metal loss, and you want to see cracks too. And, and that way somebody doesn't have to crawl through the pipe. You send the pig instead.
Right. Right. And so this is interesting. So this is very much a operational side of things. We the part of our life cycle that we oftentimes don't talk about in product lifecycle management. But I can also imagine, computers, digital transformation is a buzzword we all hear today. Computers have gotten a lot faster and a lot cheaper. Right. Can you describe, where you were doing your finite element analysis, say over the last 10 years, what has improved your ability to predict? I mean, the computers have gotten a lot less expensive, right?
Right.
So what has that enabled?
Right. So if you think back, say 10 or more years back to your old X386
X388, dude, you and I are old enough to know what you mean, but there's a lot of people listening that may not know.
Right. So if you think back to those old computers, it was a big deal at that time to maybe have a hard drive with 100 megabytes, not the terabyte or 2 terabytes you have in your laptop now. Mm-hmm. And so initially, doing these kind of fracture mechanics analyses, the model fidelity was much lower than it is today. And we were lucky if we could run a couple of linear elastic analyses overnight.
Right.
That was great. Come back in the morning and, wow, I have 2 or 3 model answers. That's fantastic. Where now we can run hundreds and hundreds of those analyses today, or we can increase the model fidelity. So more memory, more RAM in your computer, bigger hard drives. That allows us to have much greater improvement in the model fidelity. And then we can query the results better. And so better models are great. And then also being able to run more models to do case studies. So rather than just a single 1 or 2 points of results, now we want to see a wide trend. And then, go ahead.
Well, and then do you ever use it to say to, like, I'm thinking like in a pipeline company, to suggest to them, well, you could extend the life of your pipeline, but you've got to lower the fluid's pressure by 5%. If you do that, you gain a year or two. You do that kind of what if analysis?
Absolutely. Yeah. The what if analysis or parametric analysis is really useful, that you can run the analysis as is based on the current findings and operating conditions of the pipeline or the jet engine or the rocket engine or the pressure vessel in the refinery, whatever the equipment is. And then say, well, what if we change something? And that's really up to the client to know, can they reduce the pressure by 5%? Could they maybe change the temperature? In fracture mechanics, the material toughness property is temperature dependent. So if they could warm up the structure first, they'd have better toughness and it could tolerate a larger crack. So sometimes you can move the pieces around to get a better outcome under the current conditions, for sure. And then you can even extend that into the Monte Carlo probabilistic analysis.
Right.
That if you have uncertainties in a material data, when you get material testing data, there's always some scatter in the measured values. So you could assign a probability distribution to that, and then use the computer to run millions, tens of millions of cases, and that'll be enough data to give you probabilities of failure. And so you could decide, is 1 in 1,000, 1 in 1,000,000 the probability that you're willing to live with? And you can tie that into your risk for your life cycle management as your equipment ages and gets a little bit of wear and tear on it.
That's interesting. One of my sons has chosen to be an iron worker, which is kind of interesting. But some of these predictions, I being a simulation guy, we've had interesting debates with each other about weld properties, right? Weld quality. And he's currently working at a site where they are examining, probably ultrasonic, or maybe it's something else, some of the welds, and they're saying, no, you got to take the weld out and redo it. And I'm sure it's a life prediction thing, right?
Right.
So it's kind of interesting, and it's a pumping station, so it's a lot of natural grass moves around at least the middle of the country. And here in Michigan, it comes from Canada a lot of times. So interesting. So given how fast computers are changing, do you think, I could imagine you and the gentleman you mentioned his textbook, I can imagine you've got a list of problems you wish you could solve if you just had a bigger memory and a faster computer. Do you guys have such a list? I mean, give us a teaser. What's going to happen next?
Well, I think we can continue to increase the model fidelity. So right now, our material models, if you think of like stress versus strain behavior, that's a pretty macroscopic description of what the atoms are doing. So you can imagine is that we can get better and better model fidelity. We'd be able to even model maybe the microscopic scale of the metals, since metals have these tiny little crystalline cells in them, the little grain structure. Maybe we could get down to that level and model the grain structure and maybe improve the predictions that way.
So what kind of applications of mechanical systems does that matter most in? For instance, is it the quote unquote harsh environment of space, but it's consistent? Or is it something down here on the planet or underground? What would benefit, which area would benefit most with this more atomic level analysis?
I think a lot of areas could benefit. Certainly extreme operating conditions, like in space, there's a big thermal swing in those kind of structures, but harsh conditions with chemicals and high temperatures. Another kind of damage that can lead to cracking is the creep damage, where a metal at high temperature, it will over time slowly deform, and the metallurgy will change and little voids will form between those grain boundaries. If you could model that in more detail, that would really improve some of those microscopic crack development prediction into when it's going to form into a macroscopic crack that we can see. And if you can predict that or find that, that can give you more time. You'd be able to find the crack sooner. You'd have more time to decide what you're going to do with repairs or reinforcement in your structure. And then being able to do the analyses quicker. There's still a number of types of fracture mechanics analyses that we do that can take several hours or even to run overnight, even on current fast workstations. It used to be that those analyses really weren't even feasible. Now they're feasible, but take hours. Maybe in the future, it'll be something you can run over lunchtime and have your answer when you come back from lunch.
Well, yeah, and I lived through that in the 10 years I played with simulation at a car company. And in particular, it's interesting in all companies to ask the question, well, what did they choose to insource versus outsource? And in the case of a car company, where the torque goes from an engine or motor, whatever, to the wheels, everything along that load path is probably your secret sauce. And I was always impressed by our metallurgists and guys cutting gears, right? How would we figure out the best gear geometry to make sure those hairline cracks never formed that you mentioned earlier, right? So it's kind of fascinating. And we'd have high-level models for torque management, but then we'd have these fracture models for making sure that the way the teeth are shaped in a gear, and even the way they're finished, right, cut and then polished, that was done to a particular tolerance to prevent fractures. So it's really kind of interesting. So in your business, so you're advisors and measurement engineers and simulation folks in this area of fracture mechanics. What kind of companies typically come to you? And you know, one of the things we're interested in the Digital Enterprise Society is how can we help the smaller companies, the smaller manufacturing companies, embrace some of these digital technologies? So first, I'm curious, what kind of companies come and how do you think you could help the smaller guys?
Right. That's part of where our consulting is focused, is that a smaller manufacturing company, smaller product development, they may not be able to devote resources to studying fracture mechanics because it is a somewhat involved topic. Larger companies are probably doing their own engineering. So if you imagine you mentioned automotive, if they have a big enough engineering and metallurgy department, they're probably doing their own engineering and analysis and testing. So I think having smaller companies come and be able to help them with maybe their occasional questions, that can be really helpful to spread that knowledge out. And within fracture mechanics, my experience has been that automotive is really interested in that crack initiation, but just about every other industry, whether it's energy, power plants, nuclear plants, aerospace, which can be things like rocket engines or fuel tanks. You really don't want to have a crack in your fuel tank.
Yeah, really bad things happen when you do that, right?
Right. And even like big storage tanks, maybe you drive by a big chemical plant or refinery and you see these large cylindrical storage tanks. That's another area that the analysis can be applied. That's called a hydrotest exemption, where you can do analysis and that replaces physical testing.
Yeah.
So that's an area where the digital is maybe coming ahead of the testing, but physical testing is still needed. So hopefully all of that information can feed into each little company and help them improve or at least understand maybe why a crack had formed, and then they can maybe make changes in their methodology.
This is one of the reasons companies hire folks with your kind of background, either as a consultant, if they can't afford the investment, to your point, or in the case of big industrial companies like a car company, well, there's a department of people that have your kind of credentials, and that's their thing. And they used to do it all through physical tests and measurement, ultrasonic, whatever. And then they were challenged, well, the physical test takes too long. We don't have time to run all that. So how do you put it all into simulation so that you can, and then it's just a matter of how much money you want to spend on high performance computing, which has become a commodity, right? I mean, it was really expensive not that long ago. And now everybody's got it in their palm. It's really quite amazing. Well, any last words of advice you might have to a small manufacturer? And I don't even know they would know to contact Quest Integrity, but what would you like to tell them?
Well, if they're building something mechanical made out of metal, because other materials like composite materials, that's a whole, even another realm of examination. But metal structures, I think there's a lot you can do with simulation to, at a starting point, even just use finite element analysis to understand what your stresses are, maybe at those small radii in a gear or some other fitting, maybe understand stresses in welds. Welds are a challenge for sure. That there's a lot they can do. They don't just have to rely entirely on empirical or testing analysis. I think that could be helpful for them.
And folks like you can, because you've got the background and you've looked at different kinds of materials, you can quickly help them navigate, well, what are your choices? One thing that's been popular on the show has been this notion about 3D printing or if you will, additive manufacturing. Right. Have you guys also started to venture into that? Because the molecular structure changes based upon, drops of material and melting them together as opposed to casting a block and milling away all the material.
Right. Only a little bit so far. I think that could become a larger area as AM structural components maybe age and develop. I think at the point now, probably additive manufacturing is probably more focused on crack initiation type analysis to make sure that the shapes and the curves in that structure are not causing a local high stress. But over time, we may need to model larger cracks in those kind of structures.
Interesting. Well, this has been fascinating, Greg, and I appreciate you reaching out. You're an example of somebody out there who heard about the Digital Enterprise Society and said, hey, let's talk about this. And it's been really fun having this conversation. And I still have an observation. It's us aerospace guys that are helping push the envelope in simulation and PLM. So here's another example. So thanks for joining us. And Thom, I'll hand it back to you.
Yeah, thank you very much. And Greg, thanks for being here on the show. One of the things I like to do before we end these episodes is we get really smart people who've been really successful, like you, and we have a lot of listeners who are at the early stage of their careers. They're trying to grow a career, in this whole sort of PLM world. What advice do you have for maybe someone who's, younger in their career, who's looking at where can I go? There's so many different things you can do in this crazy business. What advice do you have for somebody?
That's a good question, Thom. I would say for students, either in engineering or in sciences, or maybe even young engineers, that understanding the fundamental concepts will really serve as a great foundation, since you really don't know where you're going to end up. Like you said, there's so many different interesting topics, interesting kind of jobs that you can do. In my case, when we're doing this fracture mechanics analysis, we need to know things about material properties, especially for metals. We need to know about stress and strain. We need to know about computer software. We write our own software, so even as an engineer, I'm ending up writing lots of software to do these kind of calculations. So understanding the basic physics and math is really important. And then to add to that, as an engineer, I think English wasn't my most favorite topic in school, but being able to write pretty clearly and concisely is important when you're creating reports and memos and maybe even conference papers when you're going to share information that you've done. I think that would be great. And then finally, if they get a chance, even as students or early engineers, ask their company or their manager if they can attend conferences. ASME has some really good conferences. I've enjoyed the NAFEMS conferences. That lets you learn what other people are doing when new things are coming along, and even to make contacts with other people.
That's a really good point. That's where we came from, right? The former PLM world, which was more about CAD and PDM, and then simulation. NAFEMS is one of those forums where everybody who is anybody in simulation, they've been there or they go there.
Right.
So it's a really good point. At your early point in your career, you should reach out to these things and then just find what resonates. I found it interesting you were pointing out your interest in physics, but then you became an aerospace engineer. Your background and mine are very similar. I remember asking my college as a freshman, well, I really like this. And they said, oh, if you really want to do physics, you got to go to the engineering school. It's
right.
As opposed to pure science, right? So that's a plug for engineering schools. But anyways, it's nice having you on board. Thanks again, Greg.
Yeah, thank you.
Sure. Good to talk with you, Thom and Craig.
Thank you so much. And you know, we always say this, or often say this on the show, and that is if there's a topic that you'd like to hear more about, or if there's something that you're an expert on, be sure to reach out to the Digital Enterprise Society podcast, because this show, hey, it exists for you. I mean, Craig and I have a lot of fun hosting it, but this show is all about the people who tune in and listen. So please share with us your ideas, and remember to join us here every single week for more thoughts, ideas, and information in and around product lifecycle management. The Digital Enterprise Society, it is the place for the exchange of ideas around digital manufacturing tools. Go right now and check us out at digitalenterprisesociety.org.
You've been listening to the Digital Enterprise Society podcast. Learn more about what you've heard here today at digitalenterprisesociety.org. Join us again next week for more connection without boundaries and creation without limits.